I am Anuradha Mathur. I teach physics at Modern School Vasant Vihar in New Delhi. In the previous unit, we had learnt about force doing work, and we learnt how to calculate this work by finding the dot product of force vector and the displacement vector. In this unit, we are going to learn about how can forces do work, what gives them this ability. Now, the ability to do work is called energy. So, today we are going to concentrate on energy giving mechanical work. In the previous unit on kinematics and dynamics, you learnt about laws of motion and equations of motion, and from there we can connect the work done to this ability. Let us see how. The equations of motion which you had studied earlier, where v was the final velocity attained by a body which started off with the initial velocity of u and moved with an acceleration of a for time t. Another equation of motion that we had was given like this, where s was the displacement, and we could consolidate all this in this form: v square is equal to u square plus 2as. Now, let us see how this can be giving us the value for work done. If force F is applied on a body of mass m, an acceleration of a is produced, and from looking at this last equation, that is this one, we can say if our body starts from rest, so u equals 0. So, v square is equal to 2as, and if we multiplied both sides by m just to get this ma factor here, so that we could recognize the force in this equation, we multiplied by m. So, this could be written as 2 f s. Now, the quantity 2 could be taken on the other side, and it will give us half m v square, which is equal to f dot s. Now, this result becomes exceptionally important. Why is that? Because on the right hand side we have work, and on this side we have a figure which is relating mass and velocity to this factor. Now, the quantity half m v square is said to be the kinetic energy. The reason why we say kinetic, because it would be associated with any object of mass m moving with a certain speed of v. So, all moving systems, because they have mass and if they have a certain velocity, you could talk about its kinetic energy. The kinetic energy could be constant if both m and v are constant. It could be changing if the value of v is changing. Now, how does this help us connecting it to work? So, work done is equal to the kinetic energy that the body possessed. But supposing u was not equal to 0. So, this equation that we wrote, half m v square minus 0 to be equal to f s, would now be m v square minus half m u square, which would be my work done. This is called the work energy theorem, which tells us that the amount of work done is equal to the change in kinetic energy. This is a very useful equation, because we can use it to find the value of work in case we know the change in kinetic energy, and we can find out loss in work done by forces that we do not know. We can do an example to this effect and find that out. Supposing I imagine a cliff. So, we have half m v square equal to f s. Now, in this we have completely ignored, or we have said that the body started from rest, that means u was equal to 0. But supposing u was not equal to 0, we would then have our equation as the change in kinetic energy to be equal to the work done. So, the change in energy is equal to the work done, and this is our work energy theorem. Let us see how we can use this for some very interesting ways to calculate things that we usually cannot do. Suppose we start off to find out the work done by some unknown force and use our work energy theorem to do so. For example, if we have a cliff and height of the cliff is say 1 kilometer and a pebble, a small pebble falls off from here. Now, what will be the forces that would act on that pebble? There will be the gravitational pull, which will be its weight, and there will be lot of resistances on account of air resistance. Now, the moment it strikes this base from here, we would know how much work it has done, because we would know the displacement, we already know the force on it, and we can also find out the kinetic energy at which it strikes. So, the change in its kinetic energy and this should be equal. Whatever is lost would be the work done by this air resistance. Let the mass of the small stone or the pebble be equal to 5 grams. It is very, very small, and say the distance it travels is 1 kilometer. So, if it drops from rest, its initial kinetic energy is going to be 0, and say it strikes the ground at a speed of 50 meters per second, then its final kinetic energy is known to us, which is going to be half mass we will need to convert into kilograms. So, 10 raised power minus 3 multiplied by 50 square. So, this value of kinetic energy, if you calculate, will come out to be equal to 6.75 joules. On the other hand, from the cliff we can find out what is the work done. So, work done is going to be equal to mass of the stone multiplied by g. So, let us take that as 10. So, 10 raised power of minus 3 to convert it into kilogram, that multiplied by 10 meters per second square for g value into 1 kilometer, which is 10 raised power of 3 meters. So, the work done if we calculate would be equal to 5 into 10 raised power of minus 3 to make it into kilogram, 10 meters per second square, and 1 kilometer 10 raised power of 3 works out to 50 joules. So, 50 joules and 6.75 joules, this means there is a lot of loss in the work done. So, where has that gone? So, that must have been the work done by the resistive forces, which from here we can say 50 minus 6.75 joules is the work done by the resistive forces, which we could not have calculated. We could not have been able to see this either unless we use the work energy theorem. Let us consider some more typical examples, but before we go on to do so, we have to explain one more type of mechanical energy, which is the potential energy. Now, potential energy of any system can be on account of two factors. One, because of its position in relation to another object or another level or another condition, and the second one is configuration. Now, we will deal with this separately so that we get a better understanding of it. What do we mean by position and what do we mean by configuration? We have all played with bow and arrow, rubber bands and throwing pellets. What happens in that? We stretch the rubber band, and when we release the rubber band, the pellet or the stone or the marble moves out, like in the case of a bow and arrow, the arrow shoots out the moment we release the bow. Likewise, because of position of a body with respect to say a ground level or a certain level, you store a certain amount of energy in it, by virtue of which it is capable of doing some work. Both these are termed as potential energy, because they allow the system or the body to do actual mechanical movement. So, there is kinetic energy and potential energy, and both of them form together the mechanical energy of a body. Now, we are going to learn about energy conservation. Since we are talking about mechanical energy, the two energies involved are potential and kinetic energy. They are interchangeable, they convert from one form to the other. I am going to show you an example. I am going to show you a small demo of a wheel that stores the energy and successively converts it into kinetic energy and stores potential energy again. You can see it for yourself how this is going to happen. So, we have got two types of mechanical energy, the potential energy and the kinetic energy. For a body, these two should be interchangeable, and that is exactly what happens when we drop a body from a height. It acquires speed and therefore also possesses kinetic energy till such time as it is at the lowest point and is about to touch the base. For example, when we have a body dropping from here and it started from rest, all it had was potential energy and it gains speed, and as it is just about to strike, mv square becomes its only energy, which is kinetic energy. What happens to the potential energy at this point? Potential energy mgs converts totally into kinetic energy. We have many examples like this, and we can calculate the value of net value of energy at any of these positions by finding out the speed at these different locations here. So, that will give us the value for kinetic energy, and correspondingly to the height of this we can also find the value for potential energy. Why did we say this value is mgh? Because this height is h and m is the mass of an object. Why did we say potential energy here is 0? Because in reference to this point, the height of the body located here is h, and therefore, this can be taken as 0. So, this is a relative term. This needs to be understood that potential energy is in reference to this line. If we take the baseline lower, then of course, the value of h changes, and so does the value for potential energy. Now, at this location, let us say, which is at a height of say h dash, the value for potential energy is mg h dash. What will be the corresponding value for kinetic energy? If we need to find that out, we must know what is the velocity when we cover this distance. This distance here is h minus h dash. So, in order to find that out, we can use our equation of motion. V square is equal to 0 because the body is just dropping down. It had no kinetic energy, therefore, its initial velocity is 0, and this minus 2 g, minus we have taken because it is in the Cartesian coordinate towards the negative side, and this displacement is also negative. So, we can put another minus sign and put this as h minus h dash, and this entire value becomes 2 g h minus h dash. So, if I want to find the kinetic energy, this would be given by half m and 2 g h minus h dash. If you notice, this value m g h minus h dash when added on to m g h dash will give us the value of m g h. So, the total kinetic energy from here to here is going to change, but the net kinetic energy plus the potential energy is going to be the same at every point over here. So, though kinetic energy and potential energy are changing, the total value still remains the same. Now, this is true only for conservative forces. What is meant by conservative forces? If a force is doing work, whether conservative or non-conservative, how does it matter? But a conservative force would be one for which the final and the initial position is the only thing that is important in calculation of the work done. That means, the displacement between the final and the initial position is the only consideration for finding out whatever be the path. That means, there is no change in its energy to be accounted for in its entire path from initial to final position. Let us take an example of a crane which is lifting a load, and this is my hook to which some weight is attached, and notice I am going to draw for you as this crane lifts this with this pen, and the direction is going up like this. I could bring the crane round, use another way to go up. Notice the path The first path and the second path are quite different, but the value or calculation for the potential energy gained by this would only be taken from the lowest point to this highest point. So, this is not material whether you go like this to reach this position or you go straight up. For example, you could go like this. This is how the crane could go. Let it go that way. It does not matter. The track is exceptionally long because it went wavy like this, but the net height gained is this much. So, the potential energy change is equal to mgh only. I am going to show you a demo of a wheel which can be rolled up and you can give it some potential energy, and when you release it, it is going to roll down and gain kinetic energy. Because of its inertia of motion, it is going to continue to roll and roll up to again store potential energy. This exchange of potential to kinetic energy is going to go on for some time, and we are going to see how this energy is maintained and how much of it gets lost. Now, here is the black disc and suspended by two strings, and as I roll this up, storing potential energy in it. More height above the ground, more potential energy. I take it up to this point and I am ready to leave it. Watch this. As it comes down, kinetic energy, inertia of motion, and see it from the ruler, almost to the same height it goes. But after say third or fourth round up, the energy dissipates a bit more. Where do you think that energy is going? Because we say energy is conserved. It changes into other forms. There must be some friction which is causing this change. There must be some kind of torsion which is making this wheel swing more than what it should be. And so, the resistive forces must be taking away the energy, as we did in the pebble example. Now, energy can be in any form. It could be sound energy, heat, light, and of course, the mechanical energy which you have just learnt. So, when people say, oh, switch off lights, you will be conserving energy, but energy is conserved. So, what is the halla about? It is only to say that you want to save energy in its form of electrical energy, not light up a bulb and use it as light energy. So, energy conservation, learning about mechanical energy is all very, very necessary, because there are so many systems around us which make use of potential and kinetic energy changes. And of course, in the process, the resistive forces take away some of this energy and convert it into other forms. In the next unit, we are going to learn a little more of application of work energy theorem for some more real life examples.